Hello, students. Next, we will learn about the chemical composition of petroleum, resins, asphaltenes, and heteroatoms like sulfur, nitrogen, oxygen, and trace elements in petroleum. Most of these are concentrated in the vacuum residue. Therefore, the content of non-hydrocarbon compounds is quite considerable in the heavy fractions of petroleum. The heaviest part of petroleum basically consists of macromolecular gelatinous or asphalt-like substances. Gelatinous or asphalt-like substances are collectively called resin-asphaltene substances. They can be divided into resins and asphaltenes based on polarity. Gelatinous or asphalt-like substances exist in high boiling point fractions and residual oil. They are complex macromolecular compounds with fused aromatic rings as the core, connected to naphthenic rings and alkyl side chains, and containing various heteroatomic groups. The division is mainly based on the solubility of resinous and asphaltenic substances in different solvents. Asphaltenes are insoluble in low molecular weight N alkanes, generally C5 to C7, but soluble in hot benzene. The solubles are those that can dissolve in both benzene and low molecular weight N alkanes. The solubles actually include saturates, aromatics, and resins. From this, we can summarize the definitions of asphaltenes and resins. Resins have very large molecular weights, generally between 500 and 10,000. Their carbon-hydrogen ratio is between 7 and 9. They are compounds containing carbon, hydrogen, sulfur, oxygen, nitrogen, and other elements, with very complex structures. It is generally believed that the molecular structure of asphaltenes is centered on a fused aromatic ring system. This is connected to peripheral naphthenic rings and aromatic rings. The peripheral rings carry several alkyl side chains of varying lengths and different structures. The molecules contain heteroatoms like sulfur, nitrogen, oxygen, and complex metals like nickel, vanadium, and iron. The structure of asphaltenes is similar to resins, but even more complex. It is commonly a product of resins. Its molecular weight is larger than that of resins. The carbon-hydrogen ratio is around 10 to 11. Because petroleum asphaltenes and resins contain a large number of heteroatomic compounds and are non-volatile, there is currently no single analytical element capable of determining their structures. Common solvents used for separating asphaltenes include N-pentane, N-hexane, N-heptane, and petroleum ether. The content of asphaltenes separated using different solvents varies significantly. The content of N-pentane asphaltenes is higher than that of N-heptane asphaltenes. Therefore, it is necessary to specify the solvent used for separating the asphaltenes. The resin content also varies considerably depending on the analytical method. In China, the current standard is the four-component analysis of residue, saturates, aromatics, resins, and asphaltenes. Let's summarize the characteristics of resins and asphaltenes. In appearance, resins are brown to dark brown, extremely viscous liquids that flow with difficulty, or amorphous solids. They melt easily when heated. Asphaltenes are dark brown to black amorphous solids. They do not melt when heated but become brittle and crack into fragments. In terms of density, the density of resins is slightly less than 1.0. The density of asphaltenes is slightly greater than 1.0. Resins form true solutions in crude oil. Asphaltenes exist in the form of a colloidal solution. The average molecular weight of resins is generally in the range of 1,000 to 3,000. Molecular weight of asphaltenes is larger, between 3,000 to 10,000. The H/C atomic ratio of resins is between 1.4 to 1.7. The degree of condensation of asphaltenes is relatively high, between 1.1 to 1.3. Resins are generally distributed in various solvent oil products. Asphaltenes, however, are generally present in the residue. The solubility of resins is better than that of asphaltenes. Resins can dissolve in petroleum ether, while asphaltenes cannot. Except for a few crudes with very low resin and asphaltene content, with the vast majority of petroleum in reservoirs, after long-term evolution, forms a relatively stable colloidal dispersion system. The micelle structure of the petroleum colloid is shown in the figure. We can see that in the colloidal dispersion system of petroleum, the micelle core is the asphalt first phase. It forms a micelle with the asphaltene as the core and the adsorbed resins as the solvation layer. The stability condition for the colloidal dispersion system is that the dispersion medium must have sufficient stabilizers, resins, and sufficiently high aromaticity. The presence of resins prevents the further association of asphaltene molecules into aggregates and their tendency to coagulate. Factors leading to asphaltene precipitation include the following three aspects. First, low resin content results in an insufficient thickness of the formed solvation layer. Second, the structural difference between resins and asphaltenes is large, and the interaction force between them is relatively weak. Third, the aromaticity of the dispersion medium is low, or its viscosity is too low. Today we learned about the introduction and structure of resins and asphaltenes, as well as the petroleum colloidal dispersion. This concludes the content of this lesson. Goodbye, students.